So we have obtained the following solution of GR equations of motion for the matter content under consideration. dr squared 1 minus 2 kappa m of r divided by r minus r squared d omega squared, where I remind you m of r is 4 pi integral from 0 to r dx times x squared rho of x, and d nu over dr, nu is a gravitational potential, d nu over dr is defined from the following equation: 2 kappa m of r plus 8 pi r cube kappa p of r divided by r times r minus 2 kappa m of r. And there is also the condition of the stability of this solution is that r is greater than 2 or equal to kappa m of r, so there is no horizon. This guy is always has appropriate sign. And the Tolman-Oppenheimer-Volkoff condition for the stability, hydrodynamic stability of the star follows from this equation and the energy momentum conservation, and is given by this equation: P plus rho kappa m of r plus 4 pi r cube kappa p of r divided by r times r minus 2 kappa m of r. So now, well, as a side remark, let me state that this equation is on the relativistic limit when p is much smaller than rho and kappa m is m of r is much smaller than r. This equation reduces to dp over dr approximately equal to rho kappa m of r divided by r squared. Okay, now let me stress a few points about this solution. First of all, when r is greater than big R, the radius of the star, where p is equal to 0 and rho is equal to 0, this just reduces to the Schwarzschild part of the metric. And in this region, when we can solve this equation, and the result of the solution is nothing but that exponent of nu is equal to 1 minus 2 kappa m of big R divided by R. So this equation indeed again reduces to the Schwarzschild solution outside of the star. And this is another revelation of the Birkhoff theorem, the theorem that declares that static spherically symmetric solution without matter, with zero energy momentum tensor, is always Schwarzschild. And I remind you that outside of the star, energy momentum tensor is 0. So now, to go further, so the solution becomes different from Schwarzschild only inside the star, as you notice, where the energy momentum tensor is not 0 anymore. So to go further, we have to specify the equation of state. So we have to specify the dependence P on rho. The simplest equation of state is incompressible fluid. Incompressible fluid is when rho is constant, is equal to rho 0, constant, is independent of r. In this case, it is easy to integrate this equation and to find that m of r, this function is just 4 pi over 3 r cubed times rho 0. And one can solve this equation for r less than r big. The solution of this equation is given by the following function P of r. P of r is rho 0 times ratio square root of 1 minus 2 kappa 2 times kappa m divided by r minus square root of 1 minus 2 kappa m times r squared divided by r cube, and divided by square root of 1 minus 2 kappa m r squared divided by r cube minus 3 1 minus 2 kappa m r, where m here, m, which is independent of, is the total mass of the star. So it's just volume of the star times rho 0. Now, from this equation, one can see that the pressure, that the pressure in the origin, P at r equals to 0, blows up, goes to infinity, if r is equal to 9/4 kappa m, if this is obeyed. So from this, one can see that to have, well, this is a rather unphysical situation, that the pressure inside the star, inside the body of the star, blows up. So we don't want to have this situation. This is unphysical. It doesn't realize in real situations. So we expect that the maximal mass of the star with the given radius is given by 4 divided by 9 kappa r. So if mass exceeds this value, the star becomes unstable because the pressure inside it blows up. So the star becomes just unstable, and this is not realized in real situation. Now everything is ready to draw the Penrose-Carter diagram for spherical star solution. So we have to separate the two-dimensional part, relevant two-dimensional part of the metric, which is, as one can guess, is just this one, dt squared minus dr squared 1 minus 2 kappa m of r divided by r. So, and we represent this as follows. So this is just exponent up to conformal factor. We represent it like this, dt squared. Well, I mean, it's exact transformation, not up to conformal factor. I mean, I just separate the conformal factor, dr squared divided by exponent of nu of r, 1 minus 2 kappa m of r divided by r. And now recall that this is everywhere regular quantity, the one which is standing in denominator. So we represent this as follows: exponent of nu of r times dt squared minus dr bar star squared. So this is new tortoise coordinate. So this we denoted as dr star bar squared. And to find it, one has to take the integral with these functions. But it is important that by proper adjustment of the integration constant, we can make such that r bar star will be ranging from 0 to plus infinity. Notice that the regular tortoise coordinates, the ones we have already encountered, are ranging from minus infinity to plus infinity. But in that case, the denominator was singular at the horizon. Here we don't have a horizon. This thing never gets singular. This thing never gets singular. So we can adjust it to be ranging like this. And this is important. Now, dealing with these quantities and making the change to the coordinates t plus minus r bar star, and making the same transformation as we did at the lecture on Penrose diagrams, one can easily find that the Penrose diagram for this space-time is just as follows. It's just half of the square, where we have the following situation. We have this is scri plus, this is scri minus, this is asymptotic infinity, this is past infinity, past infinity, this is future infinity, and this is a body of the star. So this is R equals to big R. So this is internal side of the star. Compare this to the Penrose diagram of the Minkowski space. The Penrose diagram of the Minkowski space in the coordinates t and r, where r is greater than 0, is like this. It's just half of the square. And you remember that for the t and x, where x is ranging from minus infinity to plus infinity, we had this Penrose diagram. So for this case, we have only half of it. And for this case, similarly to this situation, we encounter this diagram. So r star bar, as r goes, as r goes to infinity, r star bar becomes approximately equal to r. So these diagrams just coincide at the asymptotic infinity, but inside, closer to the star, body of the star, they become a bit different. But geometry of the Penrose diagram is more or less the same. So Cauchy surface here, this is constant time, t constant surface looks like this. And how you call it? The world line of an observer which is fixed above the star is something like that. So this is just R constant surface. So the Penrose diagram is just obvious in this situation and not much different from the Minkowski space. Это закончилась третья часть, а сейчас будет четвертая.